I welcome you all in this presentation related with the subject materials processing fundamentals and practicals. In this particular presentation, I will be talking about the metal forming and metal forming a particular process that is called rolling. Metal forming is a bulk metal forming process which is primarily used for making the plates and sheets from the ingots, okay, which are produced after the casting. Okay. So, as far as the content is concerned of this presentation, the approach of rolling and one of the parameters related with the rolling is the thickness reduction, like how much reduction in thickness is realized after the rolling in one pass. Then the rolling stand, these are the systems which are used for the rolling purpose, and what are the various factors associated with the rolling, like the speed or the temperature conditions that will be affecting the rolling. Then the mechanics of the rolling, which means the kind of the strain experienced by the metal during the rolling, or the kind of forces which we need to apply for rolling to happen, and the kind of power which is required. So, these aspects will be covered, and then the rolling will be affecting the microstructure and mechanical properties depending upon the condition under which it is being carried out, whether it is cold rolling or hot rolling. So, as far as the approach of the rolling is concerned, in this one, as I said, this is a bulk metal forming process where significant plastic deformation is involved and primarily used for making the plates and sheets. Okay. So, these are used for making the plates or sheets of uniform cross section. So, where the thickness and the width remains constant. During the rolling, the stock material, like say this is the stock material, is passed through the rollers which are rotating in opposite direction, and these are passed through the, when these are passed through the rollers, the metal is subjected to the plastic deformation, and it will be happening through the significant reduction in the thickness of the metal coupled with the increase in length. So, width however remains constant largely. So, initially if the thickness is T1, then after the rolling the thickness is reduced to the T2. Then the reduction, we can simply, that the extent of change which is happening in terms of thickness after the rolling is T1 minus T2. This is about the change in thickness, and if we divide it with the initial thickness, then this gives us the reduction. Okay. And when it is multiplied with the 100, we get the reduction percentage. Okay. So, the how far reduction is taking place, that depends on the multiple factors, including the rolling diameter, the gap between the rollers will be determining the kind of reduction which will be taking place. So, we can see stock material is passed through a controlled gap between the rollers which are rotating in opposite direction, and inter roller stock material friction basically pushes the raw material through the rolls to cause the plastic deformation. Okay. So, this basically the friction is responsible for pushing the material to pass through the rolls and to cause the plastic deformation. A close gap between the rollers causes the plastic deformation of the stock material, which in turn causes the reduction in thickness and increase in length. So, the main objective of the rolling is to produce the plates and sheets by reducing the thickness. Okay. So, basically the reduction in thickness is realized through the rolling. It is possible that we may not get the required thickness in one pass. So, the sheet or the plate after rolling through one set of rollers may be passed through the number of other set of the rollers to until we get the desired reduction in the thickness of the sheet to be produced. Okay. So, not just passing the raw material through one set of the rolling stent will be good enough to achieve the desired thickness reduction, but it may be required to pass through the number of set of the rollers like this. Okay. About that we will be talking little in detail in the later stages. So, we know that during the rolling what happens, like initially thickness is large and width is constant, it does not change during the rolling process. So, when the material is this thick material is passed through the rollers, there is a continuous reduction in the thickness. Okay. If the width is constant, then this in turn leads to the changing velocity of the material during the rolling from entry of the material in the roll between the rollers to the exit. Okay. So, considering the constancy of the volume of the material, say given volume of the material is being passed through the rollers, which is coupled with the increase in the length and the constancy of the width, reduction in thickness and increase in length. So, considering the volume of the constancy of the stock material and almost fixed width, reduced thickness results in the increasing length and the velocity of the material during the rolling process from entry to exit. So, initially reduction in thickness is very less. So, there will be marginal increase in the velocity at the entry, then velocity will keep on increasing until the exit. That is why the velocity of the metal during the rolling process continuously changes from entry to exit. It is minimum at the entry and maximum at the exit. And to understand this, we can see if initially T1 is the thickness, W1 is the width and L1 is the length of the material, then after the rolling the realized thickness is T2, width W2 and L2 is the length. Since W1 and W2 are constant because the metal width remains constant, so we get the T1 divided by T2 is equal to L2 divided by L1. So, this L2 is significantly greater than the L1, and during the rolling process there will be continuous change in velocity of the material or speed at which it will be moving during the rolling. So, the extent of reduction in thickness in a single pass of the rolling depends on the two important factors that will be determining the kind of the maximum reduction, which is maximum reduction percentage which is possible through the rolling in one pass is given by mu square r. So, mu is the friction coefficient between the roller and the stock material. Okay. This is mu and r is the radius of the rollers. Okay. So, higher is the friction, greater will be the reduction, higher is the diameter of the roller, greater will be the reduction that is possible. Apart from this, we also try to see what is the condition of the roller in terms of the roughness and also the material properties, say percentage elongation, ductility, work hardening characteristics and yield strength. So, these are the other factors that can also dictate the maximum reduction which is possible in one pass depending upon the yield strength and the ductility to avoid the cracking or to avoid the damage to the machine or the rollers due to the high yield strength. So, theoretically there are three aspects. One is the friction coefficient, radius of rollers and the material properties. These three will be dictating the maximum reduction in the thickness that can be realized through the rolling in one pass. Okay. So, the ratio of thickness reduction in rolling, as I have just said, the ratio of change in thickness to that of the initial thickness of the plate, that is called the reduction percentage. So, T1 minus T2 divided by T1 into 100, this will be giving us the reduction percentage in thickness that will be realized. Increasing the roller diameter and the friction coefficient increases the reduction that can be realized through the rolling. And however, the mechanical properties, metallurgical factors like work hardening characteristics, yield strength and ductility, thermal softening and temperature of metal during the rolling will certainly be affecting the maximum achievable reduction. Say for example, if the material is of the high ductility, high percentage elongation, low yield strength and high stacking fault energy means the less work hardening characteristics, and if it is being done at a higher temperatures, work hardening effect is absent. So, high temperature, all these factors will be increasing the maximum possible reduction that is possible in one go. So, this is the same formula about which I have just described. Maximum reduction that is possible in rolling is mu square. So, the maximum reduction in thickness that is possible, and here we can see the mu is the friction coefficient and r is the radius of the rolls. Okay. So, now for rolling we are using the various types of the rolling stands depending upon the number of rollers which are being used. So, like when we use two rollers only, it is called two high stand rolling mill. Okay. And this is when we are using four rolls, the two rolls will be working and the two rolls will be supporting the working rollers. So, that is the case of the 4 high rolling stand. This is one way of looking at where how many rolls are there in a rolling stand to facilitate the rolling. Then other aspect is the direction, whether the material is moved just in one direction during the rolling or it is reversible. So, it is also possible like there is a reversible movement, the backward and forward movement is possible through the both clockwise and anti-clockwise movement of the rollers. So, it can be just the case where the material which is being rolled is moved in one direction or it is reversed. So, in case of the reversible rolling stand, it will be moved in both the directions. So, set of rollers used for rolling is called rolling stand, and depending upon the number of rollers we have accordingly the given number of the high rolling stand kind of thing. Then there are many variants of the rolling stands depending upon the number of rollers and the direction of the movement. Okay. So, reversible rolling stand, 2 high rolling stand, 4 high rolling stand, like that. Then rolling surface morphology and the products. Say the rollers may be simple flat surfaces. So, the flat surface rollers primarily gives us the flat plates and sheets without any specific feature on the surface. So, the surface features obtained on a rolled plate or sheet depends on the surface topography of the rollers. So, if it is flat and plain, then it will be producing the flat sheets or the plates accordingly. But if we want a specific morphology on the component surface, then accordingly we have to produce. If you want this kind of the surface morphology, then accordingly we have to use a roller morphology which is of the mirror image of the shape to be produced. So, as per the need of the surface topography of the roller, as per the need, surface topography of the roller can be of the specific profile, it can be concave, convex, to obtain the respective mirror surface in form of a gear tooth, threads, cylindrical components or the contoured surfaces on the surface of the plates or the ingots which is being processed. So, we can get the threads using rollers or we can get the gear tooth also using the rolling process. So, according to the kind of the morphology that we want on the surface which is to be generated, the surface topography of the rollers is designed accordingly. Okay. As far as the stages of the rolling is concerned, initially plates are extremely thick. Okay. So, initially what we do, we try to reduce the thickness, as much reduction in thickness is possible through the breakdown passes. So, breakdown was there are 3 stages: breakdown passes, roughening passes and the finish passes. So, in breakdown passes what is done, major change in reduction in thickness is realized. Okay. This is done usually at a much higher temperature if it is the case of the hot rolling. Okay. In roughening also further efforts are made to attain the size and shape which is close to the desired one, and in the final the finished passes or finished pass of the rolling, the final closer control over the dimensions, surface finish and properties through the microstructural control is realized. Okay. So, rolling of the stock to the final product is broadly achieved through the 3 stages. One is the breakdown pass, roughening pass and the final pass or finishing pass. So, in breakdown pass or passes results in, because not just one pass may be good enough, we may require number of passes also. So, accordingly breakdown pass or passes may be used. So, breakdown pass results in the major reduction in cross section attained through one or few stages of the rolling. Okay. In roughing pass helps to attain the shape close to the desired one, and finishing pass or passes delivers the final size, shape, also the desired set of the mechanical properties as per the need. So, here we can see we are getting the ingot from the furnace. So, this ingot is processed through the breakdown or the roughening passes, and then there will be significant reduction in thickness, then finishing passes will be given. In this case there are just say 2 stages, but here we use a large number of the rolling strands to get the desired control over the dimensions and surface finish, and once it is rolled then the things will be coiled. Okay. And then it will be made ready for the dispatch. The temperature of the material during the rolling significantly determines the maximum reduction which is possible. So, this curve what it shows, increasing the temperature allows the greater reduction. Why? Because when we increase the temperature, it will be facilitating the dynamic recovery and dynamic recrystallization. Okay. And both these will be leading to the reduced yield strength, increased ductility, and that in turn will be facilitating the significant reduction in the thickness in one pass itself. Okay. So, depending upon the temperature of the material, the reduction in thickness can be achieved to a very large variation of the degree. So, here the temperature of the stock material used for rolling determines whether it is hot rolling or cold rolling. Rolling of the material above the recrystallization temperature is known as the hot rolling, and rolling of the stock material at a high temperature softens the material by reducing the yield strength, increasing the ductility, also avoiding the strain hardening during the deformation, and these factors in turn allow the greater reduction in one pass. Conversely, hot rolling allows the greater percentage reduction in the thickness as compared to that of the cold rolling. As far as the mechanics of the rolling is concerned, so here what we can see, there is reduction in thickness. Thickness is reduced from say T1 to T2 is the final thickness. So, the true strain achieved is obtained through the log of T2 divided by T1. Okay. The force required for the rolling is obtained using the average force required for plastic deformation of the material during the rolling, because as the material is rolled, there will be, in case of the cold rolling, there is an increase in yield strength, and therefore, we need to determine the average flow stress. Okay. So, average flow stress required to cause the plastic deformation, width of the material and the length of the contact. Okay. So, here we can see the rolling force desired is obtained from the product of average flow stress, which is obtained from the strain raised to the power n divided by n plus 1. Okay. Sigma average. So, here multiplied by the contact area between the rollers and slab. So, the rolling force is obtained using, like say Fr is sigma average into the W, that is the contact area, and L. So, W is the width of the roller and or the width of the sheet which is being the rolled, and the L is the contact length, slab roller contact length, and which is obtained from the R square root of T1 minus T2 in the simplified way. R is the radius, T1 and T2 are the initial and final thicknesses respectively. Once we get the rolling force, then we can determine the torque required for facilitating the rolling, and the torque is obtained from the rolling force and the roller slab contact length. So, the typical equation which comes out for the rolling, the torque required for the rolling for each roller is T into Fr, that is the rolling force, multiplied by L by 2, that is the contact length. Okay. Power for rolling is obtained again using the torque required and angular velocity. So, the torque and the rotational speed, these two will be determining the power required for the rolling. Okay. So, the power needed for rolling rotating each roller is obtained from the torque and angular velocity omega. So, angular velocity is obtained from the 2 pi n is the rotational speed in rpm per minute, rotation per minute, that primarily depends on the rotational speed of the roller. So, omega is obtained from the 2 pi n, where n is the rpm. Okay. And the T is the torque, we have already seen that. So, the power required for each roller out of the two rollers, for one it is P is equal to T into omega. So, then we get 2 pi n T or the 2 pi n Fr. Fr is the rolling force into the L by tau. Our simplified equation becomes pi n is the rpm, F is the rolling force and L is the contact length. So, as the rolling is performed by the set of the two rollers, power required for rolling will be twice of pi n F R L. Okay. So, where P is the power required, n is the rotational speed, F R is the rolling force and L is the contact length. Okay. So, the rolling, whenever the material is subjected to the significant plastic deformation, the structure of the metal gets affected. Okay. So, depending upon the temperature conditions, the variety of the microstructural changes will be happening, if it is just cold or if it is hot rolling. Okay. So, if the rolling is done under the cold conditions, then we will see that the grains which were equaxed before the deformation, they will get elongated like this in the direction of the rolling. So, basically we get the strained and elongated grains after the cold rolling. Okay. But when the rolling is done at higher temperature conditions, so certainly during the deformation things will get elongated, but thereafter due to the high temperature again recrystallization happens. In cold rolling there is no recrystallization, and maybe minor recovery can take place if the temperature increases, otherwise there may not be any recovery also. So, in hot rolling conditions, during the rolling the material will get strained like this, but due to the higher temperature again the recrystallization will happen, and the new strain free and equaxed grain structure will be produced. Okay. So, our all that work hardening effect is lost, new grains are produced, and equaxed grains so we can say in nutshell, in cold rolling conditions strained and elongated grains are produced, which are elongated in the direction of the rolling. But in case of the equaxed grains, but in case of hot rolling, equaxed grains are produced. Okay. Now, anisotropy is the another aspect, like say if when cold rolling is done, the grains are elongated in one particular direction. So, we get much higher strength in the direction of rolling as compared to the perpendicular direction, because of this directionality in the orientation of the grains. So, grains will be, the metal will be stronger in the direction of the rolling, while the properties will be poor in the direction perpendicular to that or in the thickness direction. Okay. But when the hot rolling is done, this structure, this the deformed structure is produced during the rolling, but later on recrystallization will be producing the equaxed grain structure which are produced, and no directionality is present. So, more uniform properties are produced when the metal is subjected to the hot rolling. Another important aspect as far as the mechanical properties are concerned of the hot rolling and the cold rolling is concerned. So, this is just the mechanism which is showing. Initially the grains are equaxed, during the deformation the grains will get strained, and these will remain strained in case of the cold rolling. But in case of the hot rolling, the grains are initially say equaxed, during the deformation these will be getting strained, but later on at a high temperature, since the metal is already at high temperature, things will get recrystallized. Okay. So, new strain free grains will be produced, which will not be elongated as in case of the cold rolling. Okay. So, as far as the mechanical properties are concerned, rolling and the mechanical properties that significantly affect, rolling significantly affect the mechanical properties depending upon the conditions. Say in case of cold rolling, work hardening dominates. So, because of this very high work hardening effect, there will be significant increase in the yield strength and the hardness of the material also. But this will be happening at the cost of percentage elongation. So, the ductility will be reduced, the toughness will also be reduced. So, this is one aspect, that in the cold worked conditions metal will show the greater strength and hardness than the ductility and toughness. Okay. But when we find and if we compare this as compared to that of the hot rolling, the strength and the hardness and the ductility in terms of the hot rolling versus cold rolling, then we will find that hot rolling will be offering lower strength and the lower hardness as compared to the cold rolling, but the ductility of the hot rolled components will be much higher than the cold rolled ones. Okay. So, as far as the strength and hardness is concerned, the higher strength and hardness is realized through the cold rolling than the hot rolling. Okay. But the ductility of the cold rolled components is lesser. Ductility is high for the hot rolled steels than the cold rolled components, and the directionality is there in case of the cold rolled, but it is absent in hot rolling because of the formation of the equexed grain structure. And because of the continuous dynamic recovery and the dynamic recrystallization, there is no work hardening effect which is left in hot rolling conditions, but it is already there in case of the cold rolled condition. And since we get the recrystallized fresh grains after the hot rolling, so there is no loss of the DBTT, ductile to brittle transition temperature, just like in which was happening in case of the cold working conditions or cold or rolling conditions. So, we will see now few cases here. Say this is engineering stress strain diagram is a metal in normalized conditions, say steel in normalized conditions offers the lower strength and the greater elongation or the ductility. But when the metal is subjected to the cold rolling, then we will see increase in the reduction percentage, increases the strength, but at the cost of ductility. So, basically the cold rolling reduces the ductility and increases the strength significantly. This is a typical example of when steel in normalized condition, when subjected to the increasing amount of the reduction percentage, then what it will be doing, say this is for the normalized steel, then we are having it for the 15 percentage reduction, this is for 15% reduction, then 25% reduction, 35% reduction, 45% reduction and 60% reduction. So, 60% reduction will be causing the significant increase in the yield strength and the strength of the material, but coupled with a significant drop in the ductility or the engineering strength that is realized. Okay. Now, the rolling is done of the variety of the metals, the common metals and how their rolling is done, how these respond to the rolling. So, the steels are commonly cold rolled to achieve the higher strength and dimensional accuracy, as different steel grades offer the different work hardening behavior. Okay. For significant reductions, the hot rolling can also be done. Aluminum alloys, due to their higher ductility and lower yield strength, these aluminum alloys show easy cold rolling into thin sheets, but care must be taken to avoid the thermal damage which is generated during the rolling, because the aluminum experience a lot of softening at around 250 to the 200 degrees centigrade. So, the thermal management is extremely important to avoid the degradation in the properties of the aluminum alloys even in case of the cold rolling. Titanium alloys, these alloys are very challenging to roll due to their lower ductility and very high work hardening rate. So, these often requires special approaches for rolling the titanium alloys. And the copper alloys, copper and its alloys are highly ductile, readily hot or cold rolled, making them suitable for various applications. Now, I will summarize this presentation. In this presentation, basically I have talked about the approach of rolling and what are the various important aspects related with the rolling, like rolling stands, the stages of rolling, and what is the effect of temperature on the rolling, how the rolling affects the microstructure and mechanical properties of the rolled material. Thank you for your attention.